Kajima Technical Research Institute in Singapore. This is a research collaboration with NUS, National University of Singapore. And thank you for having me here to present an overview of our research in this field. So a quick overview of Singapore. This is the map of Singapore, and so on the further west, you see the industrial zone, which is Tuas, and then on the east side of the extreme east, you will see the airport, which is Changi. Kajima's building is located beside the airport. You will see the central business district at the south side. You can see NUS, which is at the southwest side. Hello, hello, hello. And you can also see Tampines, which is the public housing of Singapore, in the southeast side. So corresponding to that, if you see the satellite imagery, most of the built environment are very red, which is hot, while the green and blue areas are basically the natural environment of Singapore. So the government has this 2030 plan to tackle sustainability and resilience. And with that, they have targets to meet and mitigation strategies to deal with this. And for us, the focus is on solar energy, greenery, and cool paint in the Singapore environment. You can see the president of NUS planting a tree. They have a 10,000 tree initiative by 2030. So this is one way of to mitigate the heat in the campus. But you will ask, where should I plant the trees? So efficiently, effectively, you should pick places where there are hotspots or places where a lot of pedestrians are walking through. So the objective is basically to achieve carbon neutrality with the building roofs to be filled with photovoltaics. In NUS, they aggressively put solar PVs on every single building, hundreds of them in the campus. But they are also worried about the heat impact. And then we had to simulate whether the heat is really giving problems in terms of thermal comfort and with vegetation, and to study how these mitigation strategies can actually help to alleviate this heat problem. So this has been done measuring field measurements in the campus for a few years, treat as a baseline from here to 2030. How do we reduce the temperature? So you can see the paper that we have done. So basically, we do a simulation of taking the boundary conditions from WRF and then doing the CFD simulations as well as the heat measurements and simulation. So in Singapore, land is scarce, but we still can find the largest deployment of solar PV on land. This is just beside Changi Business Park, beside our building. And then also any reservoir, any water bodies you can find, they just fill up with solar PVs if possible. Yeah. So these are some of the mass scale deployments. On the building level, as mentioned by the second speaker just now, Professor Saylor actually did a review recently and compared whether solar PV is good or bad. So this is a double-edged sword. In some scenarios, they are good. In some scenarios, they are bad. So that's why we need to do this investigation, whether in Singapore's context, what would it be? So as I mentioned, in Singapore, they deploy solar PVs on land, on buildings, in the water bodies, and we're worried about the thermal comfort of the people as well as the heat island effect. Therefore, greenery and cool paint are some of the strategies to alleviate this problem. And in the campus itself, we try to do that with the integration with the solar PV and greenery. Trees definitely can reduce temperature around or close to it by shading primarily. Evapotranspiration, a little bit less. In this graph, you can see probably a quarter of it will be ET, the rest will be shading. And in Tampines, as you shown in the map just now, there is a pilot study to deploy this cool coating for the entire district of public housing. So they want to compare the cool coating deployment for the entire housing estate and then compare it with solar PV with cool coating and greenery, and to see how does it perform. So the sensors are built for the entire estate to deal with this. And then you worry about people living inside. How is their thermal comfort profile if this reflectivity goes in and affect your thermal comfort? So there will be a survey done to handle this issue. the government is also worried that people will be affected negatively. So this is what is done now in Tampines. So of course, Nippon paint is a very common paint in Singapore, which is used. But of course, we are also looking at other options like Gaina here, using ceramic beads, as well as this is a British one called Pita, high reflectivity and emissivity paint. In NUS itself, we have one building called Ventus, which has a green roof. That's where we do field measurements to compare how it performs with the solar PVs at different height elevation on it. And we see how the plant thrives under that from 1 year of basically looking through observation and measurement. And indeed, the plant requires the more daylight and sunlight it has in diffuse situation, it thrives better than in the outside. And of course, it also retains the soil moisture because you are hidden under the solar PV, so your loss of water is not as great. In Kajima's own building, on our roof, we also did the same. We want to do bifacial, single facial, cool coating, greenery integration, and compare with 9 plants. So far, we feel that some plants survive better, some do not. We want to see which species can thrive better with this integration. And this is how it looks like today with the sensors to monitor the performance of both the elevation, the heat from for the contribution to the solar PV's performance, as well as the UHI issue. So Kajima has their own soil, which is very lightweight, called care soil, which is used in the whole building to minimize the load of the concrete. And we use it a lot. And also we have this moisture retaining feature membrane, which helps to cool down the heat as well as to support the heat loss. So we also deploy this on the whole system there. And then we collect all the rainwater and use it for irrigation around all the plants indoors, at the balconies and the rooftop. So everything is being recycled as a mission for sustainability. So in terms of simulation, CFD has always been used at the highest point of all the ecosystems in the solar PV framework. And for the CFD environment for outdoors, as we know, the Europe Coast 732 and the AIJ Japan are two of the best practice guidelines. But unfortunately, these do not deal with solar PV, which is a much finer feature in the outdoor environment. So there's a challenge we need to tackle. And Professor Blocken, which is famous for combining both these guidelines, they come out with his own recommendation, which is later adopted by the Green Mark in Singapore's Green Mark CFD technical guidelines. So we had to basically start from scratch to look at all the layers of solar PV, mesh them, and do our own CFD simulation. So we had to do a proposed simplification because it is just too heavy if you want to simulate for the entire campus. And from the very detailed 5 layers, how do we simplify it down further and further down the different scales? This is important because computational cost is very expensive. So we envision that if we can validate it on the field measurement and do the simulation, we can basically go up the whole chain and handle it. And in NUS, we have Ceres, who is the specialist for solar PV research, who give us all these direct and diffuse input radiation data for the simulation. And we envision that by doing this later, we can also use it much larger scale in the LCZs, where you can consider how the full potential of solar integration vertically or horizontally, and to see what is the potential of this. For vegetation, NUS has a lot of vegetation. So this is another thing we had to challenge in the CFD simulation. We can also do a simplification depending on requirement. So in open form ecosystem, the ESI version, they have the features to deal with this as the heat source, the turbulence source, and the velocity source. NG's helix also another ecosystem, OpenFOAM, does have these features to deal with. So we are also now exploring the different canopies and how it affects this kind of shadowing, solar radiation impacts for the vegetation later when we integrate with the solar PVs. And some of the measurements we need to do are like reflectivity and emissivity of these plants, as well as to check them with thermal imaging to see the surface temperatures. So last slide, I have basically shared that solar PV is one of the most viable renewable energy in Singapore. Unfortunately, Singapore has nothing else, but the government is looking at hydrogen as an alternative. The impact of solar PV can be both negative and positive, as I have shared by Professor Saylor, and depends on different climates and different situations. So we need to investigate how does it impact in Singapore. Increasing use is basically to lower down the carbon footprint, the reliance on the current grid, and mitigation strategies to be explored to improve the performance of the solar PV, as well as the thermal comfort issue. So in terms of simulation in CFD, there is lack of CFD best practice guideline dealing with such fine details of the solar PV. So we try to do field measurement validation to simplify this process. Hopefully, we can deploy it for the simulation for the entire campus scale and validation exercise to achieve this. So we also think we can, after that, we can apply this in LCZs as solar PV potentials. That's all from me, and I'd like to basically share about the GEAR, which is our new building near Changi Business Park, which is the smartest building in Singapore with 2,000 over sensors and data points. So the solar PVs are located out there, and you are free to visit us if you are keen to look at all the sustainability, thermal, comfort, and wellness things we deploy in the building. It's a living lab to test all this kind of research in this field. Thank you very much, everyone.